Our next topic is oxidation-reduction reactions, and these are also called redox reactions for short. In these reactions, electrons are transferred from one component to the other in the course of the reaction, so that as you examine the electron count for a starting material and a product, the number of electrons will be different. As an example, here's the chemical equation of rust. This reaction takes 4 moles of iron in the presence of 3 moles of oxygen gas to make 2 moles of iron 3 oxide. Iron 3 oxide is rust. Pause the video and determine the number of electrons in the iron at the beginning of this reaction and the iron at the end of this reaction. During the process of this reaction, we're going to see the number of electrons in the iron change as we look at the iron in the starting material. On the periodic table, we see that iron's atomic number is 26. That tells us that this neutral iron in its elemental state has a total of 26 electrons. On the product side, we can look at this iron 3 oxide compound and we can figure out how many electrons the iron has. Remember that we know oxygen always forms an ion with a charge of -2. And if we have 3 oxygens in this reaction, that means my total negative charge is -6. I have 2 irons to balance all of that negative charge, so that tells me that my iron has a charge of +3. If iron in an elemental state has 26 electrons, and we know the charge of this iron in rust is +3, that means that we know that the number of electrons in the iron in the product is 23. So that from start to finish, we see that the number of electrons in the iron has changed. We started out with 26 electrons, we ended up with 23 electrons. During the course of this reaction, the iron lost 3 electrons. During the course of this reaction, the oxygen will have gained electrons, but those calculations require a little bit more understanding. The goal of this example was to show you, using information you already knew, that the number of electrons in the iron had changed. In oxidation reduction chemistry, oxidation is a process where we see a loss in the number of electrons from start to finish in a reaction. Reduction is the opposite. This is where we see a gain in the number of electrons as we look at a reaction from start to finish. Overall, these two processes go hand in hand. During a reaction, if you have something that loses electrons, something else must be there to gain the electrons. When you know that something has gained electrons during the course of the reaction, that will be because somewhere else in the reaction, something lost electrons. The two processes go hand in hand. In order to analyze oxidation reduction reactions, we're going to be looking at the calculation of oxidation states or oxidation numbers. And as we go through the calculations, we're going to be looking at the rules to allow us to calculate oxidation states or oxidation numbers for each of the components that we have in a balanced chemical equation. This will allow us to identify an oxidation process and a reduction process in a reaction. So you should have a handout from class that gives you the rules that we're going to use to determine oxidation states. You must know these rules. You must be able to use these rules in your analysis of reactions. You must memorize these rules, and you also must recognize that these rules represent a hierarchy, which means rule number 1 is more important than any other rule in the list. Rule number 2 is more important than any other rule that comes after it, and so on and so forth. And we're going to get into examples at the end of this discussion where we use that hierarchy. Our first rule tells us that the oxidation state of an atom in a free element is 0. So that anytime we have a free element in our reaction, its oxidation state is going to be 0. This is going to be a really good, really easy tool for us to use as we get into identifying reactions that are redox reactions. So that if we had a reaction that took place with iron, much like the rust reaction we just looked at, its oxidation state would be 0. If we had copper or elemental oxygen, elemental nitrogen, elemental sulfur, any of the oxidation states for those components would be 0. Rule number 2 tells us that the oxidation state of a monoatomic ion is equal to its charge. Now, in order to use rule number 2, you have to have something present as an ion all by itself. We can't just assume that all ionic compounds are going to abide by rule number 2. If we have sodium chloride, for example, in an aqueous solution, Na+, because we know it's aqueous, we know that that ion is dissolved and dissociated, we know that that ion is independent of the chloride ion in the reaction. The oxidation state of the sodium cation in that case would be +1. Same for the chloride ion. Because it's independent, because it's floating around in our solution, we could say that the oxidation state for that chloride ion is -1. Okay, Rule 3 is important. Rule 3 we're going to use a lot as we go through this discussion. Rule 3 says that the sum of the oxidation states for all atoms in a neutral molecule or formula unit is 0. So neutral molecule or formula unit is 0. That means that when we're looking at compounds like HF, this is going to allow us to write an equation. This is telling us that the oxidation state of the hydrogen in HF plus the oxidation state of the fluorine in HF must be equal to 0. We don't yet know the oxidation state of the hydrogen or the fluorine, and our rules that follow will allow us to make that determination. So that at this point, it's as though we have an equation that is x plus y equals 0. As we go through the rest of the rules, we're going to be looking to determine what x or y is from those rules. Sulfur dioxide as the next example. This is a neutral molecule. So the sum of all of the oxidation states for all of the atoms must be equal to 0. Now, when we look at all of the atoms in this molecule of SO2, we notice that we have 1 sulfur and 2 oxygens. So that as we write the equation for this process, we have to take into account that we have this subscript of 2 in sulfur dioxide, so we have to account for both of those oxygens. In this case, the oxidation state of the sulfur plus 2 times the oxidation state of the oxygen must be equal to 0. So in this case, we have an equation that is x plus 2y equals 0. And again, we're going to use the rest of the rules to help us learn what x or y is in this example. Rule number 4 is similar to Rule 3, but Rule number 4 applies to polyatomic ions. The sum of the oxidation states of all atoms in a polyatomic ion is equal to its charge. So for a polyatomic ion, the sum of those oxidation states is going to be equal to its charge. If we have the nitrate ion, as we add up the oxidation states for all of the atoms, we have the sum of the oxidation state of the nitrogen plus 3 times the oxidation state for the oxygen must be equal to -1, which is its charge. Remember that we have 3 oxygens in this ion, so we have to take into account the oxidation state for all 3 of those oxygens as we write our formula. For the ammonium ion, we have the oxidation state of the nitrogen plus 4 times the oxidation state of the hydrogen must be equal to +1. Rule number 5. This says that in a compound, a metal always has a positive oxidation state. As we look a little further, it applies to some specific metals. So the first part of Rule 5 talks about our metals in Group 1A. This applies to metals like sodium, lithium, potassium, rubidium. And our rule says that these metals will have an oxidation state of +1. So this is the first case where we're told oxidation states about a particular element. So this is where we're going to begin to get help solving the equations we set up in Rule 3 or Rule 4. So then if we were looking at an example of potassium chloride, Rule number 3 told us that the oxidation states of all atoms in a neutral molecule or formula unit was 0. So that allowed us to write this equation. The oxidation state of potassium plus the oxidation state of chlorine was equal to 0. Again, we've got an equation that says x plus y equals 0. Rule number 5 now is going to allow us to substitute in for the potassium in this equation. Rule number 5 tells us that potassium's oxidation state will be +1. So now we can substitute in for the x in this equation with a +1. So plus 1 plus y equals 0. Based on that, we know that the oxidation state for the potassium was plus 1. And we know that the oxidation state for the chlorine is minus 1 when we solve. The second part of Rule 5 tells us the metals of group 2A will have an oxidation state of plus 2. So as an example here, we could look at magnesium chloride. Rule 3 allows us to write the equation such that the oxidation state of magnesium plus 2 times the oxidation state of chlorine must be equal to 0. Again, that means we have an equation that is x plus 2y equals 0. We're looking to use our rules to identify a value for x or y and then solve for the remaining value. As we go through the rest of our rules, rule number 5 helps us. Rule number 5 allows us to substitute in for the oxidation state of the magnesium. So now we have a new equation that says plus 2 times some oxidation state of chlorine must be equal to 0. That means that we have plus 2 plus 2y equal to 0. Now we can solve. The oxidation state for the magnesium is plus 2, and the oxidation state for the chlorine in this example is minus 1. Remember that we didn't have this substance as an aqueous compound in solution. That's why we had to use the equation to solve for our oxidation states. The fact that our oxidation state of magnesium is plus 2, which is what we expect for its charge, and the oxidation state of chlorine is minus 1, also what we expect for its charge. That's not always the case. You have to be careful. Do not assume that every element is going to have an oxidation state equal to its charge, because sometimes they will, sometimes they won't. Rule 6. Rule 6 applies to several of the anions that we're going to be talking about. Rule 6 says that in a compound, the oxidation state of fluorine is minus 1. So if we were looking at an example like carbon tetrafluoride, in carbon tetrafluoride, we have 1 carbon and 4 fluorines. So our equation looks like this. The oxidation state of the carbon plus 4 times the oxidation state of the fluorine must be equal to 0. Rule number 6 then allows us to substitute in for the fluorine. So we now have an oxidation state for carbon, which we don't yet know, plus 4 times a minus 1, and we know that the sum of that equals 0. So what we know from the information that was given to us in the oxidation state rules, we know that the oxidation state of the fluorine is going to be minus 1, and we then calculate that the oxidation state of the carbon in this example is plus 4. Rule 7 says that in a compound, the oxidation state of hydrogen is plus 1. So that if we were looking at the ammonium ion, we would use rule number 4, because this is a polyatomic ion, to write our equation. The oxidation state of the nitrogen plus 4 times the oxidation state of the hydrogen must be equal to plus 1. As we go through the rest of our rules, the next rule that will help us is rule number 7. Rule number 7 allows us to substitute in for the oxidation state of the hydrogen. So we now have an equation where we have the oxidation state of the nitrogen plus 4 times a positive 1 must be equal to 1. This is essentially like having x plus 4 equals 1. We know from the rules that the oxidation state of the hydrogen here is plus 1. We then calculate from our equation that the oxidation state of the nitrogen is minus 3. Again, these oxidation states are consistent with charges that we might expect for these atoms, but that will not always be the case. Rule 8 deals with oxygen. It says that in a compound, the oxidation state of oxygen is minus 2. So we can use this rule in the example of the nitrate ion. As we look at all of our rules, rule number 1 doesn't help us write an equation for the nitrate ion because it deals with free elements. Rule number 2 deals with monoatomic ions, doesn't help us. Rule number 3 deals with neutral molecules or formula units, doesn't help us. Rule number 4 in this case is the one that's going to allow us to write the equation. And that equation is that the oxidation state of the nitrogen plus 3 times the oxidation state of the oxygen must be equal to a -1. As we go through the rest of the rules, rule number 8 is then going to allow us to substitute in for the oxidation state of the oxygen. Rule number 8 tells us that the oxidation state of the oxygen will be a -2. So now what we have is an equation where we have x minus 6 equals -1. We know from the rules that the oxidation state of the oxygen was -2. We then calculated that the oxidation state of the nitrogen was +5. Now keep in mind, oxidation states and charges may or may not have any similarities. They are not the same thing. Oxidation states help us keep track of electrons in a reaction. Charges represent the number of electrons that a particular atom has relative to the number of protons in the nucleus. In this case, that oxidation state of +5 for the nitrogen is nothing like a charge we would ever see on a nitrogen, but that is in fact its oxidation state based on the way that we followed the rules. Rule number 9 says that in a compound, the elements of group 7A have an oxidation state of -1. So the elements of group 7A are my halogens. If you recall, fluorine had its own rule in rule number 6, so that this rule applies to the other elements in group 7A, chlorine, bromine, iodine, and astatine. So this rule does not apply to fluorine. The fact that these rules are a hierarchy means that fluorine getting that oxidation state of -1 is more important than any of the other elements. So if we're looking at a compound like carbon tetrachloride, CCl4, rule number 3 allows us to write the equation for a neutral compound where the oxidation state of the carbon plus 4 times the oxidation state of the chlorine must be equal to 0. As we go through the rules, the next rule that helps us know the oxidation state of either the carbon or the chlorine is rule number 9. That's going to allow us to substitute in for the oxidation state of the chlorine, that -1. And when we do the calculation, we're going to calculate that the carbon has an oxidation state of +4. So our rules told us that the oxidation state for the chlorine was -1. We then solved the equation and calculated that the oxidation state for the carbon in this compound was +4. Rule number 10. Rule number 10 says that the elements of group 6A have an oxidation state of -2. If you look at the elements of group 6A, remember that oxygen already had its own rule in this list. Oxygen's rule was rule number 8. So that this rule applies then to the other elements of group 6A like sulfur, selenium, tellurium, and polonium. So once again, this rule does not apply to oxygen. So if we're looking to calculate the oxidation states for carbon and sulfur in carbon disulfide, CS2, Rule 3 allows us to write the equation for a neutral compound where the oxidation state of the carbon plus 2 times the oxidation state of the sulfur must be equal to 0. Rule 10 now allows us to substitute in for the oxidation state of the sulfur. We know from our rules that the oxidation state of the sulfur is going to be -2 in this compound. We then calculate that the oxidation state for the carbon is +4. Finally, rule number 11 says that the elements of group 5A have an oxidation state of -3. The elements of group 5A are those in this group. So that includes nitrogen, phosphorus, arsenic, antimony, and bismuth. So that we can use this rule to calculate the oxidation states for the carbon and the nitrogen in the cyanide ion. Rule number 4 allows us to write the equation for a polyatomic ion. So that will be the oxidation state of the carbon plus the oxidation state of the nitrogen will be equal to a -1. Rule number 11 allows me now to substitute in for the oxidation state of the nitrogen. I know from rule 11 that the oxidation state of the nitrogen will be -3. That tells me that the oxidation state of the nitrogen is -3. I can then solve the equation and know that the oxidation state of the carbon is going to be equal to a +2. Now, oxidation states, again, they help us keep track of electrons in a reaction. Sometimes they look like they're related to charges, but they're really not related to charges. So sometimes your oxidation states that you get will be identical to charges you might expect. Other times they'll be very, very different from charges you might expect. Oxidation states also depend upon exactly how the electrons are shared within a compound. So as an example, when you look at this page in front of you, you see that in one example, we have calculated an oxidation state of the nitrogen that was +5. In another example down here for the cyanide ion, we have an oxidation state for the nitrogen that's -3. So the same atoms can have very different oxidation states depending on the way the electrons are shared in that particular compound. We also see among the calculations that we have carbon's oxidation state in carbon disulfide of +4, whereas carbon's oxidation state in the cyanide ion is +2. Again, the same atom with different oxidation states that we've calculated. The oxidation states follow the rules. And for any compound where you are asked to determine oxidation states, if you follow the rules, start at rule 1, work your way through rule 11. You're writing an equation. You're looking to solve for all but one of the variables using your specific rules, and then you're looking to solve for the last one. So that if you look at this example that we did for the nitrate ion, nitrogen's oxidation state was +5. Rule 11 tells us that nitrogen will have an oxidation state of -3, but notice we didn't use rule 11 because by the time we got to rule number 8, we already had all but one of the pieces of information to solve for nitrogen's oxidation state. When we looked at the cyanide ion, as we worked our way through the rules, rule 4 allowed us to write the equation, but then because we had carbon and nitrogen as the elements present, it wasn't until we got to rule 11 that our rules told us anything about any of the elements that were present. So nitrogen got that oxidation state of -3, and then carbon got whatever was left over, which left carbon with that +2 oxidation state. Again, this is a rules-based process. If you follow the rules, if you start at rule 1 every single time, there's no reason you can't get every single question correct. What I want you to do is I want you to solve for the oxidation states of sulfate and sulfite. Make sure you know what those polyatomic ions are. Then I want you to go on and solve for sodium hydride, NaH, hydrogen peroxide, H2O2, potassium superoxide, KO2. All of the compounds that you see in this example will utilize the hierarchy of these rules, meaning that all of the elements we have across all of these compounds have a rule that deals with those elements. But as you work your way through the list, you're not going to use all of the rules. So what I want you to do is solve for the oxidation states of all of those compounds, and I'll post the solution on Blackboard.